We come across situations like these in our daily life. There is fire in one of the top floors of an apartment and a fire brigade has been called. A 110-meter ladder is put up against a building at a recommended angle of 75 degrees. The base of the ladder is about 28 meters from the building and 8 meters above the ground. How do you find at what height of the building will the ladder reach? Take a look at another situation. At a construction site, building materials like steel is being dumped into transporting van. What is the length of the largest pipe that can fit into the van? What do you observe in both these cases and how would you solve them? Pythagoras theorem comes to our rescue. In both the situations, we find that two right triangles can be drawn where the length of two sides are given. The third unknown side of the triangle can be found using the Pythagoras theorem. We have learned Pythagoras theorem in our earlier classes that in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares on the other two sides. So, by adding up the squares of the two unknown sides and taking the square root of the result, we get the third unknown side of a right-angled triangle. ABC is a right-angled triangle where angle B is equal to 90 degrees. If the length of two sides of a right-angled triangle are given, then can you determine the third unknown side of the triangle? Third unknown side of a right-angled triangle, which can be determined with the help of Pythagoras theorem that we have learnt about in our earlier classes. Let us see a simple proof of this theorem. Unit squares have been constructed on the sides of the right triangle such that the number of squares is equal to the length of the side. What do you observe? The area of the square built upon the hypotenuse of the right triangle is equal to the sum of the areas of the squares upon the remaining sides. A square plus b square is equal to c square. Substituting the known values, we get 16 plus 9 is equal to 25. This proves the Pythagoras theorem. There are many versions of the proof of the Pythagorean theorem. We shall now prove this theorem by applying the properties of similar triangles. For any right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. That is, a square plus b square is equal to c square. Pythagorean theorem got its name from the ancient Greek mathematician Pythagoras, a scholar who lived around 500 BC. He was a vivid traveler who traveled throughout Egypt, learning mathematics among other things. He was fascinated by triangles with special side ratios. He studied them a bit closer and found that in a right triangle, the two shorter sides of the triangles squared and then added together exactly equals the square of the longest side. Although he is credited in the discovery of the famous theorem, it is not possible to tell if Pythagoras is the actual author. It is believed that people noticed a special relationship between the sides of a right triangle long before Pythagoras. The Pythagorean theorem plays a significant role in many fields related to mathematics. It forms the basis of trigonometry and in its arithmetic form. It combines both geometry and algebra. There are many applications for the Pythagorean theorem. It is used in a variety of areas including carpentry, construction, in determining the magnitude of velocity of a projectile and many others. How would you prove Pythagoras theorem using the concept of similar triangles? Let us consider a right triangle ABC, right-angled at B. BD is perpendicular to the hypotenuse AC. In triangles ADB and ABC, angle A is equal to angle A, since it is common to both the triangles. Angle ADB is equal to angle ABC, that is equal to 90 degrees. Therefore, triangle ADB is similar to triangle ABC. Let us consider this as equation 1. Similarly, in triangle BDC and ABC, angle BDC is equal to angle ABC, that is equal to 90 degrees. Angle C is equal to angle C, since it is common to both triangles. Therefore, triangle BDC is similar to triangle ABC. Let us consider this as equation 2. So, from 1 and 2, triangles on both sides of the perpendicular BD are similar to the whole triangle ABC. Also, since triangle ADB is similar to triangle ABC and triangle BDC is similar to triangle ABC, so triangle ADB is similar to triangle BDC. This leads us to the theorem which states that if a perpendicular is drawn from the vertex of the right angle of a right triangle to the hypotenuse, then triangles on both sides of the perpendicular are similar to the whole triangle and to each other. In a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. ABC is a given right triangle, right-angled at B. It is required to prove that AC square is equal to AB square plus BC square. Let us draw BD perpendicular to AC. We know from previous theorem that triangle ADB is similar to triangle ABC and triangle BDC is similar to triangle ABC. Since triangle ADB is similar to triangle ABC, the corresponding sides are proportional. Therefore, AD by AB is equal to AB by AC, or AD into AC is equal to AB into AB. This implies AB square is equal to AD into AC. Consider this as equation 1. Since triangle BDC is similar to triangle ABC, the corresponding sides are proportional. Therefore, CD by BC is equal to BC by AC, or CD into AC is equal to BC into BC. This implies BC square is equal to CD into AC. Consider this as equation 2. Adding equations 1 and 2, we get AB square plus BC square is equal to AD into AC plus CD into AC, which is equal to AC into AD plus CD. Since in the above triangle ABC, AD plus BC is equal to AC. Substituting this in the above equation, we get AB square plus BC square is equal to AC square. This concept of similar triangles can be used to prove the Pythagoras theorem, which states that in a given triangle ABC, AB square plus BC square is equal to AC square. Sides of triangles are given below. Determine which of these are right triangles. A. 7 cm, 24 cm, 25 cm. B. 50 cm, 80 cm and 100 cm. We have proved from Pythagoras theorem that the sum of the squares of the smaller sides is equal to the square of the largest side. For the first set of given data, applying Pythagoras theorem, the sum of the squares of the two sides is equal to 7 square plus 24 square, which is equal to 49 plus 576, which is equal to 625, which is the square of the third side. Therefore, 7 square plus 24 square is equal to 25 square, and hence the triangle formed by 7 centimeters, 24 centimeters and 25 centimeters is a right triangle. For the second set of given data, applying Pythagoras theorem, the sum of the squares of two sides is given by 50 square plus 80 square, that is equal to 2500 plus 6400, that is equal to 8900, which is not equal to the square of the third side. Therefore, the triangle formed by the sides 50 centimeters, 80 centimeters and 100 centimeters is not a right triangle. Statement: in a triangle, if square of one side is equal to the sum of the squares of the other two sides, then the angle opposite the first side is a right angle. Here, we are given a triangle ABC in which AC square is equal to AB square plus BC square. We need to prove that angle B is equal to 90 degrees. To start with, we construct a triangle PQR, right-angled at Q, such that PQ is equal to AB and QR is equal to BC. Now, from triangle PQR, we have PR square is equal to PQ square plus QR square by Pythagoras Theorem, as angle Q is equal to 90 degrees. But PR square is equal to AB square plus BC square by construction. Let us consider this as equation 1. But it is given that AC square is equal to AB square plus BC square. Consider this as equation 2. From equations 1 and 2, we get AC is equal to PR. Now, in triangles ABC and PQR, AB is equal to PQ, that is by construction. BC is equal to QR by construction. Also, AC is equal to PR, which is proved from equation 3. By triple S congruency, triangle ABC is congruent to triangle PQR. Therefore, angle B is equal to angle Q by CPCT. But angle Q is equal to 90 degrees by construction. So, angle B is equal to 90 degrees. ABC is an equilateral triangle of side 2A. Find the length of its altitude. In right triangles ADB and triangle ADC, side AB is equal to AC, that is equal to 2A, and AD is equal to AD, since it is common. So, angle ADB is equal to angle ADC, that is equal to 90 degrees. So, triangle ADB is congruent to triangle ADC. By CPCT, we have BD is equal to DC, that is equal to A. Using Pythagoras Theorem, altitude AD can be written as AD square is equal to AB square minus BD square. Substituting the known values and simplifying, we get AD square is equal to 2A whole square minus A square, that is equal to 3A whole square. Therefore, the length of the altitude AD is equal to A root 3. YB wants to climb a ladder 10 meters long to reach a window 8 meters above the ground. Find the distance of the foot of the ladder from the base of the wall. Let AB be the ladder and A be the window. Then, the length of the ladder AB is equal to 10 meters and height of the wall AC is equal to 8 meters. ABC is a right triangle with angle C that is equal to 90 degrees. Using Pythagoras Theorem, AB square is equal to AC square plus BC square. So, BC square is equal to AB square minus AC square. Substituting the known values and simplifying, we get BC square is equal to 36. Taking square root, we get BC is equal to 6. Therefore, the distance of the foot of the ladder from the base of the wall is 6 meters. An aeroplane leaves an airport and flies due north at a speed of 1000 km per hour. At the same time, another aeroplane leaves the same airport and flies due west at a speed of 1200 km per hour. How far apart will the two planes be after 1.5 hours? Let OA be the distance covered by the first airplane and OB be the distance covered by the second aeroplane. Speed of the first aeroplane is equal to 1000 km per hour. Speed of the second aeroplane is equal to 1200 km per hour. Time taken by the aeroplane to reach point A and B respectively is 1.5 hours, that is 3/2 hours. We know that distance travelled is equal to speed into time. Substituting the known values, we get distance OA is equal to 1500 km and distance OB is equal to 1800 km. Distance between the two aeroplanes is equal to AB, that is equal to root into OA square plus OB square. Substituting the known values and simplifying, we get AB is equal to 300 root 61. So, the distance between the two aeroplanes after 1.5 hours is 2343.07 kilometers. Two poles of heights 6 meters and 11 meters stand on a plain ground. If the distance between the poles is 12 meters, find the distance between their tops. Let P and O be the two poles of height 11 meters and 6 meters respectively. The distance between the two poles is represented by AB and is equal to 12 meters. Let us determine the distance OP between the top of the poles. Draw a line from the top of the pole to point Z on the pole P. Let us determine the distance PO between the top of the poles. Consider the right triangle PZO. Distance PZ is equal to AP minus AZ. Substituting the known values and simplifying, we get PZ is equal to 5. OZ is parallel to AB and is equal to 12 meters. PO is the distance between the top of the poles P and O, which is to be determined. PO represents the hypotenuse of the right triangle PZO. Therefore, by Pythagoras theorem, PO square is equal to PZ square plus OZ square. Substituting the values and simplifying, we get PO square is equal to 169. Taking the square root, we get PO is equal to square root of 169, that is equal to 13 meters. Therefore, the distance between the top of the poles is 13 meters.